Okay, so we will end this chapter today, always with 4 vectors. We will see today some special cases or some special four vectors. As you remember from the last session, we talked about the 4 velocity, which is a 4 vector in space-time. And that has a norm which is equal to 1, as you saw it last time. So today we begin with the 4 acceleration. So another 4 vector, as you do in classical physics, you do the vector positions and acceleration, then velocities and acceleration. The same for 4 vectors. So you already know about for the 4 position vector. You already know about the 4 velocity vector. So today we will see the 4 acceleration vector. Okay, so the 4 acceleration, as you know, is defined by the derivative of the vector velocity over time. But as you know, in 4 dimension, we need to use not the time t, but the invariant of time, which is tau. So tau now is the invariant of time, not the classical time t. So you know the invariant of time, which is tau squared, which is equal to t squared minus x squared. So our d tau is the invariant of time. So we will define our 4 vector acceleration by the letter gamma, major gamma, with a vector. So gamma is equal to du. So u, you know, is the velocity vector, the 4 velocity vector over d tau. So you already saw it with the 4 velocity. So it's equal to du over d tau as the derivative in a 4D space of the vector velocity with respect to the difference of tau, d tau. So it is a 4 vector. It has 4 coordinates, beginning with the 3 spatial coordinates, gamma I. It means gamma 1, 2, and 3. So along x, y, and z. So it's gamma 1, gamma 2, gamma 3, which is by definition is equal to dui over d tau. You can always multiply it by dt over dt. So you get dui over dt times dt over d tau. And you know from the last session that dt over d tau is equal to 1 over the radical of 1 minus v squared. And d over dt of ui, you know it, it's gamma vi, so it's vi over the radical 1 minus v squared. And the zeroth coordinate, or the 4th coordinate, which is gamma 0, by definition, it's du0 over d tau. So it's du0 over dt times dt over d tau. And dt over d tau is gamma 1 over radical times du0 over dt. So it's 1 over the radical 1 minus v squared, d over dt of u0. u0 is 1 over the radical 1 minus v squared. So you have these 4 coordinates for the 4 acceleration vector. So it's gamma I from 1 to 3, and gamma 0 is the time coordinate of the acceleration. So if you continue the acceleration, gamma I is 1 over radical 1 minus v squared. I mean, the radical of 1 minus v squared is a constant. So remember that v is the speed of the frame, which is constant because the frame is in uniform translation. So the radical of 1 minus v squared could be written outside of the derivative. So you get 1 over 1 minus v squared without the radical, dvi over dt. But you know that dvi over dt is ai. So the acceleration in 3 dimensions, a1, a2, a3, or ax, ay, az. So gamma I is 1 over 1 minus v squared ai, or gamma squared ai, little gamma, so the 1 over gamma squared ai. And gamma 0, d over dt of 1 over radical 1 minus v squared. This is a constant. So it doesn't depend on time. That's a constant. V is the speed of the frame. So the derivative with respect to time is 0. So gamma 0 is equal to 0. And you should know this because you can never have an acceleration along the time axis. The time is never accelerated. You have a variation of time from one frame to another, but never an acceleration of time. So gamma 0 is always 0. You can always use it. Gamma 0 is always equal to 0. And gamma, the spatial acceleration is gamma squared times the 3D acceleration. And you also know from the 4 velocities that the norm of the velocity, u squared, is equal to 1. So if you make the derivative with respect to tau, the derivative of u squared with respect to tau is 2u times du over d tau. The derivative of 1 is 0. So 2u times du over d tau is equal to 0. Du over d tau is gamma, the acceleration, the 4 acceleration. So removing your number 2, you get, so u times gamma is equal to 0. So the product of the 4 velocity times the 4 acceleration is always equal to 0. It's an invariant, you can always use it. U times gamma is equal to 0. So it's if like the 4 velocity and the 4 acceleration are perpendicular in space-time. So the 4 velocity is perpendicular to the 4 acceleration because the scalar product of these 2 vectors is equal to 0. So when your scalar product is 0, so the 2 vectors are perpendicular in space-time. So you have to imagine how to draw it. Okay, so let's see about this 4. This is not the 4 acceleration. Now we are seeing the 4 wave vector, which is another 4 vectors that would be interesting to see in field theory, because the next phase of field theory is all about electrodynamics and electromagnetism. So if you consider an electromagnetic wave, so any wave of light traveling in a medium of refractive index n, you know that you can always define the electric field by its define the electromagnetic wave by its electric field vector, which is a function of the position vector r and the time t in its classical form, in its Newtonian form or classical form. You can always write it under complex form. So the vector E, big E, is the magnitude E0 times E, the exponential of I. This is a complex notation. The I is not the index I, it's I for the imaginary notation or the complex mathematics of KR minus omega t. or you can replace the kr minus omega t by phi, which is the phase. The phase, when we say a phase, it's the difference of phase between two electromagnetic waves that are interfering. So they will create a certain difference of phase. We call it the phase. So K is a vector that follows the same direction of propagation of light. And along this direction, of course, you would have a certain unit vector, minor UK. So U here is not the four velocity. It's the unit vector along the direction of propagation of light defined by the wave vector K. So your wave vector K is the magnitude K times the unit vector K. And the magnitude K, you know it from last year's course of electrodynamics. You know that K has a magnitude of n omega over C. So n omega over C is the magnitude of K if you are traveling in a medium with a refractive index n. In vacuum, n would be equal to 1. And if you're traveling in a medium, the refractive index would be some number which is greater than 1. So n omega over C, or just n omega if you consider C to be equal to 1. So it's n omega over C times U of UK. Omega is 2 pi f. It's the angular frequency. So you know omega is the angular frequency. So it's 2 pi times the frequency f. So our phase phi is equal to kr minus omega t, and the rest frame r. And you have phi prime, which is equal to k prime minus omega, k prime r prime minus omega prime t prime in r prime. So you have r, the rest frame phi, and phi prime in the moving frame r prime. So the phase or the phase change is responsible of any interference between the two waves. So when two waves are interfering, you will have a maximum, which is the constructive interference, and you have minimum, which is the destructive interference. So when you have two waves that are interfering, you get some bright zone next to a dark zone, so bright zone, dark zone, etc. You have a maximum of interference, a constructive interference, next to a destructive interference when two waves are interfering. This is a physical phenomenon which is a reality of physics independent of any frame. So in R and in R prime, you will observe the same interference. So this phase, this interference is not variant, it is an invariant because it follows the Maxwell laws. Maxwell laws are independent of the frames. Maxwell laws are invariant, so they are real laws of physics. So when light is propagating, is traveling in any direction, in all directions, the phase change is a law of physics. So it is invariant. So this phase will stay the same whether you go from the frame R or if you are in the frame R prime. Phi is invariant. So phi is equal to phi prime. It is an invariant of the Lorentz transformation because it depends on Maxwell laws. So phi is equal to phi prime. So if you consider in 4D, and a 4D, if you consider it in the 4D coordinates, and a 4D coordinates and a four-dimensional space of the wave vector. So you have 4 coordinates. So the coordinates k mu from 0 to 3. You have ki from 1 to 3. And you have k0, which is omega over c or I omega over c as a complex notation. So you can use it in a complex notation. So it's I omega over c k0 and ki from 1 to 3 or kx, ky, kz. Or you can just put the vector k, the 3D vector k. So in order to not confuse between the k's, you can write the 3D k as a minor k, as a lowercase k, and the 4-dimensional k or the 4-wave vector as a major k or as an uppercase k. So our phase phi could be written in the following form as the sum from 0 to 3 of k mu x mu. So you will get kr, if you begin with 1, 2, 3, kr minus omega t. So you can use both conventions. You can put omega t minus kr or kr minus omega t. So you know with the proper time, you can use t squared minus x squared or x squared minus t squared. So it depends on the convention you are using. Both are right, but the standard notation of the phase is to always begin with kr minus omega t. So the space minus the time. In order to have a form that is like the classical form, because Maxwell equations are invariant. So we keep the same notation in relativity, the same as in classical notations of Maxwell laws. So we keep it as kr minus omega. So this 4-wave vector is a 4-vector. And a 4-vector, each one of the coordinates of the 4-vector has a Lorentz transformation. So you can write your 4-vector, your 4-wave vector, 4-wave vector, in terms of a Lorentz transformation. So you put it in the form of k0, which is equal to k0 prime plus v k1 prime over radical 1 minus v squared, k1, which is equal to ek1 prime plus v k0 prime over radical 1 minus v squared, and along y and z, so k2 and k3 will stay the same. And as in terms of coordinates, it's k, the big K, which is equal to the 3-dimensional k, 1, 2, 3, and I omega, or I omega over c if you are using a c that is different from 1. So a consequence of this 4-wave vector is the aberration, which is the change in the direction of propagation of light or the apparent motion of sources of light with respect to their true position. It depends, of course, on the velocity or the speed of the observer or the speed of the source itself. So this was discovered by James Bradley, classically discovered by James Bradley some 300 years ago, and it is called an aberration. They used to call it the Bradley effect, but now the Bradley effect has some other meaning in statistics and voting statistics, nothing related to physics. So instead of calling it the Bradley effect, we now call it the aberration, the change of direction of propagation of light. So let us consider a ray of light or any electromagnetic wave traveling in a medium n prime. The mobile medium is n prime. You have a light traveling in this medium n prime. So the wave, the four-wave vector k prime is equal to n prime omega prime times the unit vector u prime of k, or omega prime over c. And the k0 or the time coordinate is omega prime, or you can remove the I, the complex notation, but you know it in your heads, you know that there is an I here as a complex notation. But you can simplify this by not putting your I, but you know that this is a complex notation. So in the frame R, in the rest frame, for an observer in the frame R, K would be some K times the unit vector in R and omega in R. So for a propagation, so we will see how this K would change in the frame R. So let us consider a propagation in a plane XY. When I say the plane XY, it means it's along an angle theta with X. So we will see the plane XY and X prime, Y prime, and R prime. So the unit vectors in this frame or in these frames are in R prime, you have U prime of K, which is on X, you know, the measure of the unit vector is always 1. So it's 1 cosine theta prime on X prime and 1 sine theta prime over Y prime, etc. 0 on Z, and cosine on X, sine on Y, and 0 on Z. So if you you know how to make, so if you have a frame, you have a frame and you have a unit vector. So the projection here, you have here theta. So the projection here is cosine, and the projection here is sine. You know this. I won't spend time on this. You already know it. So the aberration. So K, if you go back to K, K is so it's K times the unit vector. It's K cosine theta, K sine theta. It's the coordinate X of K. So it's K1 cosine theta, K2 sine theta, 0, omega. The fourth coordinate is omega. And K prime is N prime omega prime cosine theta prime, N prime omega prime sine theta prime. So the measure is the same, N prime omega prime. 0 on Z and omega prime or on the time axis. So if we consider the Lorentz transformation on K1, so K1 is K1 prime plus V K0 prime over the radical of 1 minus V squared. K1 is K cosine theta, and K1 prime is N prime omega prime cosine theta prime plus V. K0 prime is omega prime over the radical of 1 minus V squared. And if you also take the Y coordinate, since we are working in an XY plane, so if we take the Y coordinate, K2 is equal to K2 prime. So K sine theta is equal to N prime omega prime sine theta prime. We have two equations. So we have now a cosine, and an equation with cosine, and an equation with sine. So if you divide these equations, you will get a tangent. Because when you need to compare two different directions in R and R prime, the most direct way and the most easiest way is to compare the tangent. To compare tangent theta to tangent theta prime, or the cosine and the sine. But classically, and the most direct way is to compare the tangents. So if you divide this equation by this equation, so you have a sine over a cosine, and you can simplify your k, you can remove your k. So you have sine theta over cosine theta, which is equal to n omega prime sine theta prime divided by this quantity. So it is multiplied by the inverse of the quantity. So it's times radical 1 minus v squared over n prime omega prime cosine theta prime plus v omega prime. Okay, so your sine over cosine is tangent theta. Here you have an omega prime, and here you can put an omega prime as a common factor, so you can remove your omega prime. So you get tangent theta with removing the omega prime as a common factor. It's n prime sine theta prime over n prime cosine theta prime plus v times the radical of 1 minus v squared. So it's sine theta prime. If we remove the n prime, so if you put n prime here as a common factor and you remove it with the upper n prime, you will get cosine theta prime plus v over n prime. So by simplifying by an n prime, radical 1 minus v squared. If you put a cosine theta prime outside as a common factor, you have to divide here by cosine theta prime. So you will get sine theta prime over cosine theta prime times 1 plus v over n prime cosine theta prime. So we just put a cosine theta prime outside, so you have to divide here by cosine theta times the radical of 1 minus v squared. So now you have a sine theta prime over a cosine theta prime. So you can compare tangent theta to tangent theta prime. So finally you get tangent theta is equal to tangent theta prime times the radical of 1 minus v squared over 1 plus v over n prime over cosine theta prime. And always in vacuum, you can replace n and n prime by 1. So you get tangent theta is equal to tangent theta prime over 1 plus v over cosine theta prime times the radical of 1 minus v squared. Okay, so now you have a tangent theta as a function of tangent theta prime. Okay, it's not a very pretty equation. It's a little bit complicated, but this is the equation to compare tangent theta to tangent theta prime. Now we will try to simplify this this equation, because it's not a pretty equation. We will try now to make a more simplified equation. And if you want to simplify it, you will have to go to a Newtonian case, or the case of very low velocities. So tangent theta is equal to tangent theta prime. If you put your denominator upside, you will put it as a power of -1. So let's go back to the initial equation. The denominator is 1 plus v over cosine theta prime. If you put it on the upper side, it's the same but to the power -1. So here is tangent theta prime. times the radical of 1 minus v squared times 1 plus v over cosine theta prime to the power minus 1. So it's 1 over, so it's the same. It's 1 over 1 plus v over cosine theta. Tangent theta prime, radical 1 minus v squared. If you are at very low velocities, so your v is very small. So v over cosine theta prime, it's like what? It's like when you say it's 1 plus epsilon to the power minus 1. So you make your expansion as a mathematical Taylor expansion of this quantity. So it's 1 minus v over cosine theta prime plus etc. You have negligible quantities after the v over cosine theta prime. Okay? So also the radical of 1 minus v squared at low velocities tends to 1, because your v squared is actually a v squared over c squared. And for very small velocities, your v squared tends to 0. So the radical is almost 1. So you will have a tangent theta, which is equal to tangent theta prime times 1 minus v over cosine theta. So tangent theta minus tangent theta prime is approximately equal to minus v sine theta prime over cosine theta prime squared, because you multiply by the tangent theta prime. So we'll get sine up there and another cosine on the denominator. So it's cosine theta prime squared. Okay, you can remove your minus by putting tangent theta prime minus tangent theta, which is equal to v sine theta prime. 1 over cosine squared is equal to 1 plus tangent squared. Okay, so you don't have to remember this, but you know it from trigonometry. 1 over cosine squared is equal to 1 plus tangent squared. This is an easy equation. You can remember it. 1 over cosine squared is always equal to 1 plus tangent squared. So your tangent theta prime minus tangent of theta over 1 plus tangent squared theta prime is equal to v sine theta prime. And also, if you go back to trigonometry, you have tangent theta prime minus tangent theta over 1 plus tangent squared is almost equal, for small angles, is almost equal to theta prime minus theta. So you can replace it to get a theta prime minus theta, which is equal to v sine theta. Okay? So your delta theta, the difference of angle between r and r prime, is equal to v sine theta prime, or v over c sine theta. Okay, so if you are not in vacuum, in a medium where you have a refractive index that is equal to 1, that is equal to n prime, sorry. So your delta theta would be v over n prime c sine theta. This is as a classical formula found classically for low velocity by James Bradley in 1727. So some 300 years ago. This was found classically. You see, it's an approximation for low velocities found by James Bradley. So this is a classical aberration formula. We found it using 4 vectors. James Bradley found it using Newtonian mechanics. But you get the same result because it is an approximation of the relativistic formula in the Newtonian case at very low velocity. Okay, so this was the propagation in an XY plane. So we only considered K1 and K2. But in space-time, we also have the K0. So if we go back to the zeroth coordinate of the wave vector, the K0, and the Lorentz transformation is equal to K0 prime plus V K1 prime over the radical of 1 minus V squared. So if you replace each quantity by its value, so omega K0 prime is omega prime, V K1 prime is N prime omega prime, or just omega prime in vacuum, over the radical of 1 minus V squared. You can put the omega prime as a common factor. So you will stay with 1 plus V N prime over the radical of 1 minus V squared. So omega is equal to omega prime times 1 plus V N prime over radical 1 minus V squared. If you turn this into frequencies, you know your angular frequency omega, which is 2 pi f, and the omega prime, which is 2 pi f prime. So you replace your omegas by 2 pi f and f prime. So 2 pi f is equal to 2 pi f prime, 1 plus p n prime over the radical of 1 minus v squared. So you remove the 2 pi, you will get a final equation that gives you the frequency in the rest frame as a function of the frequency in the mobile frame. F is equal to f prime times 1 plus v n prime over the radical of 1 minus v squared. Okay, this is the Doppler effect. When you have a frequency in terms of another frequency in another frame, this would be a Doppler effect. This is the relativistic Doppler effect. You know about classical Doppler effect from first year when you took the course of waves and the course of waves at first year when you saw the Doppler effect with sound waves, the Newtonian Doppler effect. Now it's a relativistic Doppler effect, which you will see in the next slides that we have an additional factor into this Doppler effect. So you have your Doppler effect, f equals f prime, etc., 1 plus v n prime over the radical. You have two types of Doppler effects in relativity. You have the longitudinal Doppler effect, and you have the transversal Doppler effect. Let's begin with the longitudinal Doppler effect. The longitudinal Doppler effect is when light is traveling in the same direction of the source. So you have your observer, which is the frame, the rest frame R, observing a source of light, S, so along a certain direction. And if the source is mobile with a velocity v, so let us suppose you are observing a mobile star or any mobile source of light traveling with a speed v in this direction, and it is emitting light towards the rest observer, the observer of rest. So it is emitting light in this direction. So the unit vector u is in this direction. So the angle between v and u theta prime is equal to pi. So V times U prime is equal to minus the cosine of pi, which is -1. So it's minus V. You replace it in the Doppler equation. So F is equal to F minus V n prime, because V times the unit vector is -1. So it's minus V n prime over the radical of 1 minus V squared. So your F is equal to F prime times 1 minus V over radical 1 minus V squared, which is the radical of 1 minus V over radical of 1 plus V. You can simplify by the radical of 1 minus V, and you will have another radical of 1 minus V over radical of 1 plus V. So your F is equal to F prime times the radical of 1 minus V over 1 plus V. In terms of wavelengths, which is the inverse of the frequency, you will get lambda is equal to lambda prime radical of 1 plus V over 1 minus V, or V over C. Okay, so I care about the frequencies more than about wavelengths. So if you look at F, it is equal to F prime radical of 1 minus V over 1 plus V. The numerator is less than the denominator. So F is less than F prime. Your observer here at rest observes a frequency that is less than the original frequency F prime, especially when your source is receding. So you know your source is moving away from the observer. So the source is receding. In this case, the observer will see less frequency. The observer at rest will see less frequency. So a decrease in the frequency, which we call the redshift. You don't care if the light has a red color or not. It's just a way to say that the frequency is decreasing. So when the frequency is decreasing, we call it a redshift. Whether it is colored red or any other color. When the frequency is decreasing, we call it a redshift. So it is a case of longitudinal Doppler, where the source is moving away from the observer and emitting light towards the observer. This is the first case of the longitudinal Doppler. The second case of the longitudinal Doppler is when the source is approaching. So you have your same observer in R. You have your source of light S. And this time, the source is approaching with the speed V and also emitting light in the same direction. So the unit vector U is always U of K is also in this direction. So the angle between V and UK is 0. So cosine 0 is +1. So V times the unit vector is plus V. Replacing in the Doppler equation, so F is equal to F prime times 1 plus V over radical of 1 minus V squared. So it's the radical of 1 minus V times 1 plus V. You simplify by a radical of 1 plus V, you will get F prime times the radical of 1 plus V over the radical of 1 minus V. In terms of wavelengths, it's lambda, which is equal to lambda prime radical of 1 minus V over 1 plus V. If you see here, the numerator is greater than the denominator. So your F is bigger than F prime. Here you have an increase of the frequency F. So F is increasing. It's what we call the blue shift. It's the blue shift. When the frequency is increasing, we call it the blue shift. This is the Doppler effect when your source is approaching. So if the source of light is approaching the observer, you will observe a blue shift, which is an increase of the frequency. Okay. Okay. Always was the longitudinal Doppler effect. For low speeds, you know that for low speeds, your radical of 1 minus v squared tends to 1. So you will end up by the following equation. For the first case, when the source is receding, you get f equals to f prime times 1 minus v. And for the second case, when the source is approaching, you get f, which is equal to f prime times 1 plus v, which is the second case when the source is approaching. Okay, so this is the classical Doppler, the Newtonian Doppler. The second Doppler here only observed in relativity, which is the transversal Doppler. So if you have your observer, you have the direction of the trajectory of your source of light. Now your source of light is emitting light perpendicularly to the direction of motion, in this direction or in this direction. It doesn't depend if it is receding or approaching with a speed v. It emits light perpendicularly at an angle of pi over 2 or an angle of 3 pi over 2. So it's perpendicular to the direction of motion of the source of light. Light is emitted perpendicularly to the trajectory of the source. Here, v times u is 0 because you have the product, the scalar product of two perpendicular directions or two perpendicular vectors, which is 0. So you replace in the Doppler formula, you will get f is equal to f prime, just f prime, over the radical of 1 minus v squared. It's gamma f prime, to put it in terms of gamma. And in terms of wavelengths, it's lambda, which is equal to lambda prime times the radical of 1 minus v squared. This observation is independent of the medium. It's independent of the refractive index of n or n prime or any refractive index. So the transversal Doppler does not depend on any medium or if the source is receding or approaching. It's the same. And the approximation for low speeds, you know, radical of 1 minus v squared, it's times of radical of 1 minus v squared to the power. So here you can replace it up here by 1 minus v squared to the power minus half. So if you have the expansion, it is 1 minus times minus plus half v squared, the plus, etc. You get very small quantities. We only take the second order quantity. So for low speeds, the approximation is f equals f prime times 1 plus half v squared. This is a second order phenomenon not observed in classical mechanics, because the Newtonian calculations, Newtonian mechanics, does not make an expansion for approximate values. So it stops at 1. You don't have this 1 half v squared. So for Newton, transversal frequency are always equal. For Newton, F equals F prime, and a transversal, if the light is emitted transversely. But in relativity, and doing this expansion for low speeds, this approximation, you will have an additional quantity, which is half v squared. So F is not equal to F prime, it's equal to F prime times 1 plus half v squared. So also transversely, you have a change of the frequency, and you have a Doppler effect. Only could be measured in classical, in relativistic mechanics. Okay, so this is the end of the chapter. Next time, I will give you some notions about covariant and contravariant indices and the difference between them. And we will do some exercises in a live session. So exercises will be in a live session. I will send you an email about the date and the time. Okay.